Good afternoon, everybody, and welcome to the March edition of the AESIN Tech Talk. And I'm very pleased to introduce our special guest today. He is Dr. Daniel S. Fowler, and he is an assistant professor in the field of secure and resilient system design within the Secure Cyber Systems Research Group at WMG at the University of Warwick. After serving a B.Eng honours degree in computer and control system engineering, he had a career designing software and systems architectures for a variety of industrial and business organisations before switching to research. He obtained a master's degree in forensic computing and a PhD degree in automotive cyber security. All the degrees were awarded by Coventry University. At WMG, he has aided the engineering and delivery of several innovative UK funding cyber security projects. He contributes, to the open source community through software and has written more than 300 public articles. He is a chartered engineer and a member of the IET and ACM. His talk title today is Project 𝘧𝗲𝗰, Assessing Capability, Enhanced Microprocessors for Future Cyber Resilient Automotive Systems. He joins us today from Solihull. So Dan, the floor is yours.
Thank you. Okay, I'll share my screen. Okay, so yes, I'm Daniel Fowler. I work in the Secure Cyber Systems Research Group at WMG. And this is about Project 𝘧𝗲𝗰 and WMG's involvement within it. It's subtitled Assessment of Capability Enhanced Microprocessors for Future Cyber Resilient Automotive Systems. And we'll cover exactly what that means as we progress. For those who don't know WMG, there's a QR code there if you want more information. There'll be some QR codes on some of the slides for further information. So we're an applied research and education faculty of the University of Warwick. Our focus is on industry and business impact through R&D and skills provision. And we have relationships with lots of companies. We provide degree education, apprentice, undergraduate, postgraduate research levels. We run short courses, and WMG as a faculty covers multiple engineering disciplines, so we have good experience across many disciplines.
Dan, can I just jump in? We can't see your slides just yet.
Oh yeah, I'm sharing it.
That's it. All right. Sorry to interrupt, Dan. On you go.
Okay. WMG is a well-respected faculty within the University of Warwick for many of the technical engineering disciplines that we cover. So 𝘧𝗲𝗰, there's several partners within 𝘧𝗲𝗲. There's ourselves. We are going to be responsible for a demonstrator for the project. Thales is the lead partner, and they are doing a lot of work in various areas, which I'll cover. And TechWorks through AESIN is providing dissemination, and you should already start seeing some information from the project appear on the AESIN website. And funding for the project is via Innovate UK. What do we mean by 𝘧𝗲𝗰? Well, it's resilience within the automotive space. 𝘧𝗲𝗰 builds on other automotive cyber resilience projects, and you can get the outputs from those previous projects by going to the 𝘧𝗶𝗃 website. There's a QR code there if you're interested. So we're really interested in the ecosystem of resilience for our software-controlled physical systems. So we're talking about the world's cyber physical systems, our cars, our automated transportation factories, medical devices. Our world is increasingly digitized and has been for quite some time now. And because we're dealing with cyber systems that are linked to the physical world, we can no longer rely on traditional enterprise-style cybersecurity, which was very much based on passive monitoring and a reactive defense. What we want our CPSs to do is operate safely when under a cyber attack and demonstrate what we call cyber resilience. A CPS must resist attacks and degrade safely if it's operationally, functionally compromised. And as an example of this, to illustrate the issues we have, so this is looking at contributions to the CVE database, so the common vulnerabilities and exposures. And this chart shows along the bottom that as the years go by, we're seeing a steady increase in the type of memory vulnerabilities that we experience within systems. Now, this is not to say that we're not making safe systems. What it means is that the sheer volume of systems out there means that the number of vulnerabilities will increase over time because we're just dealing with more systems and more software. So the people that want to attack our systems can still find the holes that are in the software. As an example of this, so here are some well-known companies, and they're acknowledging that there are memory issue bugs. So with the Chromium projects, our Chrome browser and the Chromium operating system, you see that memory type bugs account for, in total, about just under 70% of the bugs that they get reported. And for Microsoft, again, it's around a 70% number, and that number's stayed fairly static over the years. And Android, common operating system within phones, memory bugs are about 50% of the bugs that they get reported. So that's an ongoing issue that we have to deal with. In the beginning, I talked about capability in enhanced microprocessors. What do we actually mean by that? Well, if on the left there we got the traditional way that microprocessors work when they access memory. So you have a memory access register within the CPU, and it will put an address onto the memory bus when it's trying to pull the code and the data that makes up our software within our systems. When it pulls that data and code into the CPU, it uses some sort of pointer to access that. And it is manipulation of these pointers which is the root of many of the memory issues that we have with the security of our software-based systems. So what does a capability enhanced processor do? Effectively, what it does, it adds additional capabilities to our memory accesses. The example given here is the capability of restricting the pointer range. So it's given a lower bound and upper bound. So it's these capabilities are the form of tags onto the memory access. And it gives the hardware, this is at a hardware level we're talking about, so this is not software. These capabilities are implemented on hardware. It gives more protection to the memories, to the memory access. One capability design, and the design we're looking at is the 𝘬𝘵 design from SRY International and the University of Cambridge. Since about 2010, they've been looking at this capability design, and it's been slowly maturing. ARM have taken this design, and as part of the Digital Security by Design program within the UK, they have developed the Morello prototype system on chip and a development board that adopts the 𝘬𝘵 design, the capability hardware enhanced RISC instructions. And what we're interested in are such capability enhanced microprocessors suitable for embedded device microcontrollers. For example, vehicle electronic control units. Let's dig a little bit deeper into what the 𝘬𝘵 architecture does. So 𝘬𝘵 pointers are twice the size of traditional software pointers. For example, on a 64-bit system, they might be 128 bits long. plus what they call a validity tag bit. So if the capabilities of the pointer are misused, then that validity tag bit can be flipped, and that means that the hardware knows that register, that address register, is no longer valid, and they can then throw an error, and that can be used by the software to indicate that a problem exists. There's another part of the capabilities which we call permissions, and the permissions allow some sort of token to be added to a memory address, and the token allows you to effectively tag data structures within memory or program functions within memory. And then when, for this example, the token 0 is added to a memory structure. And when the memory address is trying to access that part of the memory, the hardware can check that the tokens are valid. For example, for token number 1 in this example wouldn't match the token on the memory, and therefore the memory address will not be allowed, the memory access will not be allowed. So again, that's another type of capability that's available within this sort of hardware. So what does 𝘬𝘕 enable? Well, 𝘬𝘕 enables fine-grained memory protection for C and C++ style languages. It allows security for a variety of operational models within software, from objects to processes, so from memory and code. It can provide software compartments, effectively ring-fencing code. And all these capabilities increase the exploit chain length that attackers must find and exploit. So the type of vulnerabilities that have been plaguing systems for quite a while should be reduced. That is the aim of capability-enabled hardware. Of course, this comes with trade-offs. Now, the actual overhead within the hardware isn't extreme. It's up to 5%, although software that uses a lot of pointers, memory accesses, it could be greater than that. Its design has been thought of in terms of compatibility. So existing code bases can be compiled and run on 𝘬𝘕 type hardware. But you do need to know how the 𝘬𝘕 architecture works to really take full advantage of the capabilities that these processors provide. And there's a table there that shows that additional instructions are needed and need to be included within software to fully take advantage of these capabilities. So the 𝘧𝗲𝘂 project is not only about looking at these ECU, these hardwares for vehicle ECUs and similar cyber physical systems. This is new technology. It has implications. So the project, through the lead partner 𝘧𝗵, is looking at the economic and business implications that this entails. There are existing tools available now that support this hardware, mainly based on open source tools. As I said, it requires additional knowledge, so there are training considerations for future developers. And how is it going to impact the entire supply chain? It's the intellectual property providers who provide us with compilers, software libraries, tools, testing, equipment, even the secure coding guidelines can be impacted. And then we have the semiconductor and chip companies and the tier suppliers, the people who are producing the electronics and the parts and modules within the supply chain. And ultimately, it's the manufacturers themselves, and in the automotive space, this is the vehicle manufacturers. I mean, how will it impact them, new technology hardware at the chip level? So we're talking about structural changes required to the engineering processes for these groups of people within the supply chain. And alongside this, we have ethical, insurance, and legal issues to consider if organisations do think they can rely on chip hardware for all their security concerns, because security is not just about the chip hardware and the software. It's a bigger issue. It's a multifaceted issue, and it's something that we're all going to be wrestling with for the future. So what do we need for the project? Well, we need some sort of example demonstrator we can show that we can use to engage with the community. Braking used to be a fairly simple function. You basically put a friction surface against the wheel to stop the car. But as technology has moved on, we've gone beyond that simple system. Even beyond the system of a few years ago, where we introduced ECUs into cars to control braking with sensors and electronic controlled hydraulic pumps for the ABS systems. We've gone far beyond that now. We look at the vehicle system these days. It's part of a very complex network internal infrastructure. We have communications between various elements of the vehicle. So the braking system is talking to the engine, it's talking to the cruise control, it's informing the passenger of the status of the braking and the vehicle. You have the diagnostics interface, and today cars are connected. They're connected to back-end services. So you have these potential paths from the wheel to almost anywhere within the vehicle. So it's a very complex environment that we're dealing with, and on top of that, we now have self-driving vehicles. We're throwing in artificial intelligence, so we just increase the complexity as we develop these systems. And we're already seeing the impact. So the system complexity does impact the braking safety. There's a couple of examples here. They're fairly recent examples. So in October last year, GM Cruise had to halt their robotaxi service after their artificial intelligence failed to identify that they had hit a pedestrian, and the pedestrian was dragged for several meters under the vehicle. So that goes to show that the whole system can impact the braking. Another recent example was when a guy in the UK could not stop his car. His car just developed some sort of fault while he was driving, and it was stuck at 30 miles an hour. In the end, he had to run into the back of a police van to bring the vehicle to a halt. So is this increasing complexity making software and hardware testing? Is it harder to find these edge cases that could happen in the real world? And can the cherry-type microcontrollers with their memory-based design, memory-based capabilities, improve the situation? Will they be able to flag errors easier than existing software does? So these are the sort of economic and business implications that the project wants to look at. Of course, it's not only the systems themselves. The fact that they're connected brings the threat of cyber attacks. I think the February AESIN TechTalk was all about the cyber implications of our vehicles, and there are various groups out there who want to attack our systems. So we have the geopolitical situation with nation states and their own cyber attack capabilities, and we're very familiar with the ransomware, criminal organizations deploying ransomware on mainly corporate networks. There's no reason to say in the future that they may target fleets of vehicles. And there are other types of groups that are engaged in cyber activity, which we need to be aware of. And because of the complexity of the modern vehicle, we have multiple attack points. So we can attack these systems from various points. It's not as simply as just connecting. When you connect your phone to your car, that's the only attack point. There are far more, and there's been plenty of evidence of that over the last 10, 20 years. But this is what we're dealing with. We're dealing with complex systems that are subject to cyber threats, and we need ways to deal with this complexity and handle this complexity as we move forward. So for the 𝘬𝘺𝘠 project, we are building a demonstrator to engage with the industry. We want to talk about this issue of complexity and what it means for our systems moving forward. What are the policies that the standards bodies and people like AESIN and other industrial organizations that are in this space, and the governments, what do they really need to think about? Even the legal profession, what does it need to think about when it comes to handling this complexity in software? And what does it mean in our industry, in our businesses as we move forward? So we're hoping to have this demonstrator ready, the first iteration ready for the AESIN Gaydon conference in July. So we're hoping that you can come along and engage with us and talk about this issue. And certainly we want to listen to other viewpoints on how we deal with the topics that we're addressing within 𝘳𝑎𝑢𝑡𝑜. So we're building a simulator based on the 𝘠𝘺𝘠𝘐 tech software, and it will be linked to a 𝘬𝘺𝑚 chip, which currently sits within a Morello board within a PC style case, but we will be running on that board an ABS model, a braking model that's written in C, and it effectively acts as a braking ECU, a 𝘬𝘺-based ECU, which will communicate with the 𝘠𝘺𝑚 simulator for its braking source and as a sync for the output from the ABS model. And what we can use this demonstrator for, so we have our demonstrator with its controls and its inputs and outputs. There's the 𝘬𝘺 chip as the ECU. It will enable us to visualize the ECU, the 𝘬𝘺 chip in action, and it will also be able to then try and perform some attacks on this ECU, play and replay software and I/O attacks that are common that we see in the wild against CPS, cyber physical systems. And that will allow us to gather some evidence, collect some data, do some visualizations of what's happening within the software, and we will then use that data to produce some evidence-based reports. So these types of memory issues are now getting more attention. So the US Office for National Cyber recently produced a report which mentioned 𝘬𝘺𝘺. So these sort of technologies are gaining traction. ARM itself has its memory tagging extension, which is a former capability, and that is now being deployed in the new Android Pixel 8 phone. So these sort of CPU type capabilities to reduce memory vulnerabilities are gaining traction. So that's it really for my presentation today on the 𝘳𝑎𝑢𝑡𝑜 project. I certainly want to engage with the community and see how you think you can handle complexity, how you think tools can help. So please do get in touch if you want to discuss these issues with me. Thank you very much.
Thank you very much, Dan Fowler. And Dan just mentioned it not so long ago. The 2024 AESIN conference takes place on July the 11th in Gaydon at the British Motor Museum. Any and all details are available via aesin.org.uk/conference. And if you're watching this broadcast live, the URL is in the chat facility on Zoom. Wednesday, the 17th of April, is the date of the next AESIN TechTalk. Our guest will be Matthew Howell of 𝘳𝘺𝗠𝗠𝗠𝗠𝗠𝗠𝗠𝗠𝗠𝗠𝗠𝗠𝗠𝗠𝗠𝗠𝗠𝗠𝗠𝗠𝗠𝗠𝗠Phas talk title will be Intellectual Property for Automotive Electronics, Why, How, and When. For further details of that one, and in fact, all of the Tech Talks for this year, go to AESIN.org.uk and look at the events section. So we'll now get on with the Q&A section of today's broadcast, and I'll get things underway by asking Dan a couple of questions of my own. So Dan, how do you feel about the complexity of the software world we now live in terms of threats?
Because software is, well, it really goes back to the fact that we have this wonderful thing called a computer, which was really the first reprogrammable machine. It's a machine that can effectively do anything, and that's the power. That's what's given us the world we live in today in terms of technology. It has accelerated our economics growth. It has accelerated what we can do within in business. It's made us more efficient. But the machine, because of its programmability, is its weakness. In fact, if you can find a hole in the software and get a foothold onto the machine, you're able to change the program, and that's effectively what attackers do. They change the program with any computer, and because we are now managed to miniaturize computers to such a degree that they're everywhere, the attack surface is huge. And the IT Software Foundation, for example, they tackle this problem head on. They realize that these embedded devices are a security issue within our society. So the complexity is immense, and that's why we need to carry on looking at how we can address that through new software, new hardware, such as these capability enhanced microprocessors.
Okay, thanks for that, Dan. One more question from myself. How confident are you in terms of the new chip architecture in the marketplace?
Well, these capability ideas have been around for a long time. I mean, if you look back in the literature, you can find them in some of the 1970s experimental operating systems for mainframes. And so they've been around for a long time, and with some ideas, it does take a while for them to gain traction. But because of the problem with software bugs, memory-related software bugs, companies are now looking at these sort of additional capabilities within the hardware. So I'm pretty confident that we'll see these capabilities coming into hardware, but I think it may well be over a longer period rather than a short period. As I've shown in one of the slides, Google phones, the latest Google phones do now have some memory tagging features introduced into them. And I'm sure we'll start seeing those sort of features appear in other commodity chips as time moves on. And it's just supplementing other hardware designs that we've seen being rolled out. So we've had trusted computing modules. We're seeing hardware security modules added to chips. So these all help. And what we need to do, particularly as WMG at the University of Warwick tries to do, is ensure that future engineers and future programmers are ready to use these new capabilities when they appear in the market.
All right, thanks for that, Dan. Question from John, who says, many thanks. Is there something specific about 𝘠𝗵 simulator that makes it particularly useful for Res Auto compared to other vehicle simulators, for example, Carla?
Yeah, what we like about the 𝘠𝗵 simulator is that it's standalone. It doesn't require any external libraries for it to work, and also it's got quite good programmability at the low level, so we can get into the braking system, which is what we want access to, and we can effectively insert our ECU into it. So we can replace the code within the simulator with a link back to our PC, so that makes it attractive to us.
All right, time for just one more question, Dan. This is from Rob. What is the route to market for Cherry, in your opinion?
It's getting the semiconductor buy-in, the semiconductor companies to buy in. There are different. I mean, ARM has been funded by the government to produce the ARM chip, but it's a bit of a chicken and egg. So we need demand from software developers and software houses for these sort of capabilities. We also need demand from the hardware manufacturers, the people that deploy the components. We need that demand to really put pressure on the chip manufacturers to include those capabilities. And also the chip manufacturers can use it as a marketing aim as well. If they implement these capabilities, it'll make the value of their chips more attractive to the market.
Dr. Daniel S. Fowler in Solihull, thank you very much for your time and for your presentation today for this AESIN Tech Talk. The next AESIN Tech Talk, as mentioned earlier, will be on Wednesday, the 17th of April. And our guest for that will be Matthew Howell, of 𝘳𝗵𝗵 𝗧𝗹𝗸, and the top title is Intellectual Property for Automotive Electronics, Why, How, and When. Further details of that can be found in the events section of AESIN.org.uk. So you can actually register for that one if you're watching this live. The link to register is in the Zoom chat facility. And if you go to the events section of AESIN.org.uk, you can also register there as well. Thank you very much to everybody watching today, and we'll see you next month for another AESIN Tech Talk.